Welcome to this lecture on rotordynamics. Okay. As you know, every machine actually is essentially comprising of a shaft which is supported on bearings. And invariably it rotates, and there could be a housing, etc., and so on. If I just draw one half, and this shaft could be carrying a disc. So, these are my bearings, bearing 2, bearing 1. This is my disc, which could be an impeller, and this is the rotating shaft, and this is the machine casing. And so, there is another one on this side which I am not drawing. Now, in rotordynamics we see, and if you think of any machine, be it a electric motor, be it a pump, be it a gearbox, be it a IC engine, essentially each one of them consists of a shaft, and the shafts will not be there in air, they are supported on bearings. And when the shafts rotate, they could be carrying a disc or an impeller. Think of a large turbine, think of a compressor, think of an aircraft engine. Okay. So, all these machines or rotating machines have a shaft which is supported on bearings. So, rotordynamics studies the dynamics of such rotating shafts which are subjected to different conditions. Now, what are the conditions here? It is essentially how does the dynamic behavior of the shaft, how does it affect the machine's, loosely saying, vibration level, machine stability, etc. Now, in rotordynamics we will see these bearings play a very important role, and there are many simple models to study this, and one is a simple Jeffcott rotor, which is nothing but a shaft supported on bearings carrying a disc. So, if you think of this shaft which has a load W acting, and then this is supported on some stiffness, because these bearings give certain stiffness K, you will see the natural frequency of this system omega n is nothing but, in this case, 2 K by m, where W is equal to mg. So, you see this system has a natural frequency, okay, and which is influenced obviously by the mass carried by this shaft and this support stiffness. So, support stiffness is very important, and they control what is known as the natural frequency of the system. Now, we know from our basic theory on vibrations that any external forcing frequency omega, if it is equal to omega n, we have the condition of resonance, right. So, at resonance what happens? The amplitude of the motion would increase. This amplitude could come to a level that at resonance maybe this is this, okay, and these amplitudes is maybe undesirable, okay, some amplitude A which is undesirable. And now, there are many reasons why this amplitude has to be under control. So, because imagine if this was a long shaft and it was carrying a set of blades, and this came across a casing. So, what could happen once this touches the casing, it will give a phenomenon of rub. If this flexes, this bow flexes too much, it could induce fatigue stress on the shaft, and there could be failure. So, this will be giving you an idea the importance of understanding the dynamics of a rotating shaft which is supported on bearings, and then all the designs associated with ensuring that I have a stable design of the rotating system is what we will be studying in rotordynamics. So, what are the objectives of rotordynamics? One is predicting the critical speed, because these shafts could be having a natural frequency because of rotation. So, one should always avoid operating the shaft at the critical speeds. We can do certain design modifications to change the critical speeds. So, playing around with the stiffness. Okay. Predicting the natural frequencies of torsional vibrations. So far we had studied about the linear vibrations, but in any torsional vibration systems, I have what is known as the inertia term plus the damping term and the stiffness term, which is equal to the external torque in a rotating system. So, this theta is the angular displacement, and the subsequent derivatives are the angular velocity and then angular accelerations. So, even in a rotating shafts, I would not like to have high motions or unstable motions or large motions and so on. And then many things happen in these shafts. We have assumed that this shaft to be concentric between the two bearings. That means, the geometric center of all the systems are in the same line. Imagine if there was an unbalance or an eccentricity in this shaft in terms of a geometric eccentricity E. So, what is going to happen to these displacements at certain speeds omega is again a factor which we need to study. In fact, if this eccentricity E is E, the displacement is given by A is equal to E r square by 1 minus r square okay. A is the amplitude of vibration at any r, where r is nothing but omega by omega n. So, at r is equal to 1, you will see this amplitude is again controlled by A at r is equal to 1 is nothing but E by 2 zeta. So, this is an important conclusion from vibrations, that at resonance all the amplitudes are controlled by playing around with the damping. So, we can introduce damping in the system to reduce this amplitude, and in rotordynamics people design on systems wherein they can have some external damping played around at the bearing stiffnesses, and we will come to this later on. So, another reason was once I told one was eccentricity, where there is a difference in the geometric centers, another is the mass unbalance. We will talk about mass unbalance in the later chapters, but in the eccentricity case we can find out the amplitude at any point r given by this expression, where zeta is equal to c by root over 2 k m. You already know that. And r is equal to omega n. Omega n is the natural frequency of the system, and omega is the external forcing frequency. Of course, this is circular frequency. So, the unit is radians per second and not hertz, where f is equal to omega by 2 pi, and this is given in hertz. Okay. Now, what happens in rotordynamics? We also would like to find out the amplitudes of synchronous vibration caused by rotor imbalance and predict these threshold speeds and vibration frequencies for dynamic instability. So, I just explained you with 1 degree of freedom system, but you will see these shafts are strictly not rigid. If they were rigid, they would not have any deflections. Okay. So, they are elastic. So, that is why they deform. While rotation, they will bow out. Okay. Now, question is, because I could divide this shaft into many degrees of freedom. So, I can have, strictly speaking, theoretically speaking, infinite degrees of freedom system, but no, within a limited range there will be many natural frequencies of this shaft. So, there is a very important diagram which is used in rotordynamics, which is known as Campbell diagram, which plots the rotational speed to the different natural frequency of the system. So, if a shaft like this will have many natural frequencies, these are all horizontal lines. Okay. So, I can have the rotational speed such that this is my rotational speed. This is one crossover, this is another crossover. So, these are regions where I should not operate my machines. So, maybe this is one N1 RPM, N2 RPM, N3 RPM, and this is maybe the natural frequency omega 1, omega 2, omega 3. So, this region is only the safe operating region. If you are going in this speed, the speed. So, there are regions of safe limits wherein resonance can be avoided. So, people spend a lot of trying, a lot of doing analysis to find out when they design a system, how do I find out the natural frequency of such long rotor shafts. You talk about turbines, you talk about compressors, because as an operator, you are not allowed to run at N1, because N1 speed corresponds to a natural frequency. Okay. So, you should move around and shift your N1, so that it does not interfere with the or coincident with the natural frequency of the system. So, such kind of diagrams, Campbell diagrams are developed. In fact, how can you want to do that? People use the standard techniques of finite element methods. To analyze such systems, because we obviously cannot make such analysis by actually physically constructing a shaft and going through this. So, as a machinery operator or a designer, we have to specify what is the safe limits for such machines which have multiple operating speeds, so that one avoids critical speeds. And in these conditions, you will see when particularly the speeds are very high, when you are operating a gas turbine. Okay. We cannot really start, because gas turbines typically 30,000 RPM. So, by the time you reach 0 to 30,000 RPM when you are cranking up or start up during startup, you will cross many natural frequencies. So, you are not allowed to operate it at any of the natural frequencies, otherwise resonance would occur and fatigue would set in. So, one is quickly asked to pass through these resonant conditions very quickly. Okay. And all of you must have witnessed it, particularly sitting in an aircraft. If the pilot has just started the engine and is going up, revving up to full speed, you will see they will go for regions from you will see suddenly a large vibrations and then it will disappear and so on. And so, when you feel large vibrations, that means you are just passing through the first critical speed, second critical speed and so on. So, obviously, many times, particularly in plant machineries, there is always a limit that this is the safe operating speed, and that is there for any rotating systems. So, but then one of the other objectives of the rotordynamic analysis is to suppress such dynamic instabilities. Well, the method to reduce this synchronous wheel amplitudes, obviously, if I have the balance the rotor, that means the geometric center, the mass center, they are all concentric, and change the speed, avoid the critical speed, and of course, add damping to the rotor bearing system in the case of the squeeze film dampers. Particularly, if you talk about bearings, we will come to that later on. See, some of these bearings are anti-friction bearings or the journal bearings. So, there is a certain stiffness. The anti-friction bearing stiffness is very high, order of 10 to the power 7 to 8 Newton per meter. Okay, very high, and this is being very rigid in the case of anti-friction bearings. We do not have much play in it, but if you talk of other bearing like the journal bearing or the fluid film bearing, we can have provision to add certain squeeze film dampers. We will come to that later on. So, what does this bearings support stiffness do? So, bearing support flexibility can greatly reduce the dynamic load transmitted through the bearings. Okay. This damping increases the dynamic load transmitted through the bearings at high speeds. Bearing supports keep the transmitted load within acceptable limits while traversing the critical speed, because I was telling you, once you go from 0 to 30,000 RPM, there will be many critical speeds one will be traversing through. So, one has to go through these methods. So, one good idea of controlling the stability of rotating shafts at high speeds is to play around with the bearing stiffness. And of course, there will be some supersynchronous vibrations, subsynchronous vibrations because of shaft misalignment, loose components and so on. So, this is what we are talking about, is critical speed. The response at such large, when at critical speeds, natural frequency will vary with rotating speed, and like I told you, the Campbell diagram shows a variation of natural frequencies with shaft speeds. So, we need to calculate the critical speed of rotating shaft so as to avoid issues with noise and vibration, and that is the analysis people do for large rotors. If you think of a gas turbine, okay, there will be sets of compressor blades, multiple stages of compressors, and then of course the combustion chamber and then the turbine. Okay. So, air going in and this shaft rotating at very high RPM, 30,000 RPM. So, imagine if the exhaust coming out and then you get the thrust. So, this has many critical speeds. So, if one set of critical speed, there will be a rub here. So, there will be an instability and they are supported on bearings. So, one has to design this bearing stiffness as bearings, so and the stiffnesses and damping, so that these amplitudes are within limits. So, one such study which we did with finite element method. So, this is a shaft, as you can see, right, which has been modeled in finite element model, the shaft supported on bearings. So, this is how the bearings are represented. This is the step, this is the step for the bearing and the bearing shaft, this is the shaft, main shaft, and another step and the bearings. So, you will see this is the rotational velocity in radians per second, which could be also in RPMs, and these are the different natural frequencies. So, this is the first natural frequency comes at about 400 hertz, and then the second natural frequency. So, this gives you an operating idea from the Campbell diagram that this is the only the safe limits. You have to avoid these critical speeds. So, different modes, the critical speeds are indicated here, okay, and for different ratios where it is stable, unstable, one can study this. Okay. So, if you look at this mode shape of the critical speeds of the shaft, you look here that this red means maximum displacement, that means this is bowing out like this. Okay. Now, imagine this. So, the factor which was controlling this natural frequency is, of course, if the inertia of the shaft is not to be changed, it is this bearing stiffness which would influence the natural frequencies. Okay. Now, we can do by the expression of omega n is equal to root over 2 k by m, but to be more accurate you can do finite element model and then do it, and this is the second critical speed. So, here you see there is maximum deflection. So, the shaft is flexible. So, it is going having a bow motion like this. Okay. So, there is an actually a this is an whirling will occur, and then there will be a better diagram of whirling in the subsequent classes. Okay. So, when we study rotordynamics, we design a turbo machinery first and foremost is to avoid critical speeds. Those of you who would have designed just shafts from simple strength of materials, we other than calculating the torsional strength of the shaft to withstand the external torque, we also must find out the critical speed of the shaft, so that it never operates at the critical speed, and then we are away from the critical speed. Well, minimizing the dynamic response at resonance, if critical speeds has to be traversed, when you go up to high speeds, there will be many critical speeds. So, this has to be traversed, and of course, minimizing vibration and dynamic loads transmitted to the machine structure through the entire operating speed range. Avoid turbine or compressor blade tips or seal rubs, because this rubbing would occur, as I was telling you, because of large motions. So, this is going to hit a casing. So, this rub would occur, that has to be avoided, and avoid torsional vibration resonance or torsional instability of the drivetrain system. So, these bearings play a very important role in the shaft. So, we have this rolling element bearing and the journal bearing or the fluid film bearing. So, in the rolling element bearing, as I was telling you, they have almost a constant high stiffness, but in the hydrostatic bearing or the hydrodynamic bearing, we can play around with the bearing stiffness depending on the viscosity of the oil, because depending on the eccentricity and so on. So, certain tests are done on the rotor systems, one to find out the natural frequencies. One is the static test, stiffness test. Okay. So, you will give certain force and measure the deflection. Okay. But another very important test which people do is coast up and coast down test. So, that you increase the speed from 0 to certain n RPM at a constant rate, and then or from n to 0, this is the coast up, and this is the coast down. Okay. And then the resonance test is like a bump test. We give certain force and then measure the natural response and plot its frequency domain. So, this is the first frequency, first mode, second mode, and so on, certain amplitudes. But whenever there is this coast up and coast down, we can see at certain RPM there will be high amounts of vibrations. Okay. And these are the places where resonance will occur. So, in summary, in rotordynamics, we understand the dynamics of rotating shafts, which is inherently present in any machine, and the effect of the bearing stiffness and how does the bearing stiffness play with the critical speeds of the shaft. And no shaft is actually, strictly speaking, rigid. They are flexible. So, they will have many critical speeds. So, a designer of rotordynamics would give the operator guidelines as to what are the safe operating limits of your machines. And the reason these dynamic instabilities occur because of eccentricity, because of unbalance. So, if these are not looked in total, we will have an issue wherein we could be unknowingly driving it at resonance, and it will create other machinery problems. So, some of the common fault conditions in turbo machinery, which we will be seeing later on, is imbalance, misalignment, load variation, mechanical looseness, critical speed or resonance, excessive clearance in fluid film bearings, rotor rub, oil well, and oil whipping. Okay. Well, more about this can be found in my book on machinery condition monitoring. Okay. And thank you.